Welcome to In 5 Minutes. The agenda of this clip is to understand clock distribution or clock routing, and in this clip we will also understand the H tree architecture and driver trees. We know that the clock which is generated needs to be distributed to different points on my chip. Let's take a classic example of this is the block, or this is the IC which has so many receiver points which all needs to be driven by clock. In the previous clip, we have already seen that if there are a lot of receiver points which needs to be driven by clock and they are all present at different lengths from the clock, then we know that delay tau is proportional to L square, and there will be a problem of clock skew because two receiver points might not receive its clock at the same time. So what we will do is we will try to reduce our problem by not driving individual receiver points, but try to group the receiver points and then think about a solution of driving the group in such a way that all the groups receive the clock at the same time. So suppose all of this are my receiving points of the clock. What I have done here is I have tried to group all of them into a group of 4 as an example, and now I have 4 groups which I need to drive. Understand, this distribution and clock routing is a very challenging phenomena which happens in the routing when you do physical design. In that specifically, when you do routing, this becomes quite challenging. Here we are trying to just understand in terms of layman how exactly we should try to avoid this problem. So one, we understood that there are a lot of points present, correct, that needs to be driven. We should not drive it individually because all receiver points will get a difference due to the length of the interconnect on the clock which is received by themselves. So we started grouping them. Here we have shown the groups of 4, and now I have started internal routing, or I started routing all these 4 points internally, which means that I drew vertical lines and tried to make some connections, and then so if you see, I made this connection vertically. This also I did it, this also I did it. So I've tried to internally route all my points such that my clock which needs to be driving this group should be able to drive all the groups at the same time. However, you see that I'm not able to achieve complete horizontal, or in this case complete vertical connections, because all these points are randomly placed. So grouping it randomly is not technically going to help us quite a lot. What we learned from this was we should not drive individual blocks. We should try to make them in a group and try to drive the group, but then because they are so randomly placed that internally inside the group also to route the clock would be very challenging because they are not completely in the vertical dimension or in the horizontal dimension. They are scattered all over. Similar to grouping, we also have a concept called as partitioning, where again very similar. This is my points, or these are my receiver points, where I first partition it in the horizontal direction. So I have 2 groups now. Then I partition it, so I have 4 groups now, correct? Now I have started making a 2-point group. So I have started making groups in such a way that you see here I have made a horizontal partition. So this is a 2-point group, this is a 2-point group. Again the same here, 2-point group, 2-point group. Again the same here, 2-point group, 2-point group, and so on and so forth. But again, you see that the points are so randomly placed. What we tried to achieve differently from grouping here was, there were a lot of points which needs to be driven. I connected and made a group, or I partitioned and made a group of 4. From group of 4, I made a group of 2, so that it's easier if they are in the horizontal orientation or the vertical orientation. We know that if they are both in this direction or both on this direction, if I put a clock here, it will be equidistant, so the length would be the same. And I tried achieving that, but the points are so random that the results are going to be nearly the same to the grouping technique. So again, we might partition in horizontal and vertical directions, but it's not going to yield quite a different result from grouping, and hence this itself is not a very good idea. So let's presume that somehow I got this 4 points which I need to drive, and inside that 4 points I have blocks which are placed in such a way or grouped or partitioned in such a way that they are aligned to each other either in the vertical direction or in the horizontal direction. Then what I need to do is I need to have my clock circuit sitting here, or it's like this. Suppose these are my 4 blocks, say block 1, block 2, block 3 and block 4. Then I'll put my clock circuit here so that all these 4 points are equidistant, and then internally these 4 groups can drive another 4 groups as well. So basically what we are coming up to is nothing but an H tree architecture. Let's understand this. So what I did was I placed my clock here, and these are my 4 groups, which in turn will drive another groups. So what I'm going to do is I'm going to ensure that my clock generator, or the clock which is getting generated from X, is at equal length from all these 4 groups A. That means if we see the delay, tau is nothing but length of XA, right? X2A, and X2A for all 4 is same. So tau is equal to L XA square, which means it's the same for all the 4 blocks. This 4 blocks internally can have another H tree architecture where it can drive another 4 blocks. So I'm creating super groups and super groups here, so that one clock is driving a group, which in turn is driving another group, and so on and so forth. This will work well if all your points or all your receiver points length of the interconnect is the same. That means that all your 4 receiver points are placed at equidistant from the clock generator terminal or the clock generator circuit. And very important, which we also need to know, is that delay depends on R and C, right? So the capacitance of all these 4 points, length is one of the parameter which we already took into consideration, that it has to be same. But then if this one has a higher load and this one has a lower load, then we know that for higher load more delay will take place, because delay is proportional to R into C. So we also need to ensure that the load capacitance of each of the receiver points must be same. Now technically in real time, this is a very challenging thing to ensure, correct? Because at physical level, you'll need to plan this, and physical design means the layouts, which most of you might not know how to make currently and will be studying in the future classes. People who already know, to make the layouts to ensure that the capacitance are equal is quite a challenging thing. So though this will support the geometry, let's go to the next slide, you'll understand. All receiver points can be accommodated by the geometry of H tree, but then to ensure that the capacitance at the load is the same, and to ensure that the length of the receiver point is equidistant from the clock generator point, is quite a challenging task at the physical level. Though we can use it, but if there is a better solution, we can go ahead and use that. So the next solution which we have is to use driver trees. Now what are driver trees? Basically what we do is, if we have an interconnect, I've already mentioned this in one of the previous clips, which has a length of say 100 meters, just an example, purely an example, then the delay is going to be L square, which means 100 square. So what I do is I try to break this interconnect into 2 parts. One is of 50, the other one is of 50. So delay is 50 square plus 50 square, which is less than 100 square. And when I break the interconnect, I need to ensure that I don't lose the value of my signal. And that's where I add buffers or a chain of inverters. So what I do is, this is my clock. Suppose these are all my receiver points, correct? And I want all of them to receive the clock at the same time. What I'm doing is, technically it was like this. This was my clock and this was my receiver. So in between this, or in this path, what I did was I broke the interconnect so that my delay reduces. And when I broke the interconnect, I started connecting inverters or buffers to restore the value of the signal. And I started grouping them. So a group of 4 was driven by one, a group of another 4 was driven by another inverter, 4, another group of 4, another. And this 4 in turn was being driven by my another inverter, which had clock as its input. So basically what we are trying to understand is an inverter driving some blocks, which in turn is driving some other blocks. The same thing which we understood for H tree, where you drive a group and group drives another groups, exactly the same. Now we have reduced the length of the interconnects here, and here if the values of the capacitance, which was a problem in H tree, are different, what we can do is we can size these inverters in such a way such that still all the delay or all the points can still receive the clock at the same time, and that sizing is nothing but sizing of inverters through a concept called as logical effort. So we can try to do that. This is just nothing but an internal diagram of this interconnect where I have replaced all the interconnects with the pi model of RC delay. Now I've explained the same thing. Now you might also understand that this is a symmetric circuit, you know. Sometimes the circuit might not be symmetric, and in that cases, when you try to use logical effort, it would be quite better if you use a single buffer chain. What does that mean? Suppose these are all different blocks or receiver points which needs to be driven by clock, and the entire circuit is not symmetric. So what I do is I connect a chain of inverter, if you see, from a smaller size to a larger size. That means I have sized my inverter with different values of W and L, such that my point X receives the clock in a way that it can drive all these points with a delay which is nearly equal, and that itself is a challenge. So these are some of the challenges which you face when you try to do clock distribution or clock routing. And that's the reason these days we also have heard about something called as asynchronous system. Asynchronous systems means something which does not depend on clock. We have already seen this, where you have this control signal, correct, which is coming out, and at the same time this control signal might be given to your logic block, which will have inputs and outputs. So your control signal will ask the circuit, are you ready, by sending a request. Once the circuit is ready and gives its output, it will give an acknowledgement. This is nothing but the concept of handshaking, which we have already studied, in which you don't have to be dependent on clock, because right from generating the clock to stabilizing the clock to distributing the clock at different receiver points, it's quite a challenging task. In this clip, we saw that the clock can be distributed to different receiver points by grouping them. We also saw the concept of partitioning. We saw that partitioning and grouping helps us to make the groups, but then still to drive that groups is itself a challenge. So we saw the concept of edge trees, in which we saw that the length of the interconnect, if being same, all the receiver points might receive the clock at the same time, and we also needed to ensure that the load capacitance value is same. But that itself is quite a demanding or a daunting task, and hence we moved ahead and saw the concept of driver trees and single buffer chain, and how do we need to size our inverters to the concept of logical effort by breaking the interconnect lines or by breaking the interconnects and ensuring that the delay value, or ensuring that the clock tries to reach all the points at the same time. And with all these challenges, we also saw that if we want to overcome this, or if we want to move towards an asynchronous system, we have the concept of handshaking. Hope you have followed this. Stay tuned for further clips, and thank you very much.